Hello friends, let's move on in continuation to the previous talk, and we are talking about this beautiful series of Solvay conferences that have taken a beautiful shape in the field of conversation, in the field of interaction, and posing questions that make sense and 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 refuting the questions with a pure, perfect logic. Now, where we have reached now is we have reached to a point where we will first talk about this paper that was published by Albert Einstein, Podolsky, and Rosen. And this paper is known as EPR paradox. So, EPR paradox was a kind of Einstein's greatest challenge to quantum mechanics. Uh, it was it was a challenge based on exact scientific arguments. It was not something like that posing that you don't have an interest, you feel that it's not working, and you will come up with any kind of boring opposition to deal with a situation like that. So what is happening here is Albert Einstein is coming up with his paper, and really up to this point in our journey, Einstein had challenged quantum mechanics many times. He challenged it many times, and we have gone through all these basic arguments again and again. And to our understanding, Neil Bohr had answered all his objections till now. But to be frank enough over here, Einstein was not a scientist who could give up easily. It was not that kind of personality, because he had a reason. And what he did, he believed that if quantum mechanics truly described reality, if it described the reality completely, then it should basically satisfy certain basic principles, and these basic principles, every physical theory respects. And one of those principles was locality. So we would like to understand this locality principle. Now, in order to understand this locality, I mean, let's try to understand this idea very carefully, and because it lies at the heart of everything that we're going to talk about. So let me go with this gesture. I mean, suppose you are standing in, say for example, you are standing in Srinagar, and you have a friend in Delhi, and if you clap your hands, your friend in Delhi does not instantly hear that sound. And to have made this example so simple so everybody understands it, because the answer to this question is that sound has a limited speed. I mean, sound travels through air at a very, very finite speed of the order of 340 to 350 meter per second. Now imagine you switch on some powerful flash of light. You have a light, and you switch on this flash of light, and what's going to happen over here is the light takes time. It takes time to travel. I mean, it takes 8 minutes light to move from sun to the planet Earth. So nothing is happening instantaneously across very, very large distances, because light is also going to take some time to reach the other point. So this is one of the profound lessons of Einstein's theory of relativity. The argument is this, that it takes time. And According to relativity, according to special theory of relativity, what we have is you cannot have any information, no information or not any signal or any physical influence can travel faster than the speed of light. So this principle it certainly had become one of the cornerstones of modern physics. Even though it is one of the cornerstones of the modern physics. Now, in those times, it was the only thing that was there for the fastest thing that could be found in the nature. So Einstein believed that any complete theory of nature must at least respect this principle. It must respect this principle. Now let's try to imagine a different situation, because we are trying to understand it at the basic level. Suppose I have a pair of gloves. Okay, gloves one. I have a right glove and I have a left glove. I have a pair of gloves, and one is for the left hand, as I said, and the other is for the right hand. What we have a pair of gloves. Now what I do is I place one glove in one sealed box and another glove, and I put it in another box and I seal that box. Now these two boxes, these boxes are then separated. They are separated by thousands of kilometers. You have a pair of gloves, one is on one box and the right is on the another box. Now what you do is you receive one box and I keep the other. Say for example, I'm the other one who's holding another box. The moment you open your box and you discover that your box has, say for example, it has a left hand glove, you immediately know that my box contains the right hand glove. It's quite normal, nothing special about it. Has anything mysterious happened here? No, nothing. Because you already knew about the pair of the gloves. If the right one is with someone and the left one will be another one. And the point is, nothing traveled from your box to my box. The gloves already had their identities. They had their exact identities before the boxes were opened. You exactly knew what is in the boxes. So your observation simply revealed information that was already there. There was this information, and you could automatically seek out the other part of the glove anywhere in the universe. And Einstein believed that quantum particles should behave in a similar fashion. That means, okay, whatever is going on, you must be knowing exactly what's going on. You must be knowing. Now, if two particles are separated by great distances, measuring one, if I make an act of measurement, measuring one should instantaneously change the physical state of another particle. Okay, so now what's happening? You have in 1935, Einstein joined forces with two brilliant men, with two brilliant physicists, Bohr-Podolsky and Nathan Rosen. And what they did, they together published one of the most influential papers in the history of physics. Okay. And today, all of us know today, we know it simply as I said, as EPR paper. And the purpose of the purpose was, we should intuitively look for it, the purpose of the paper was not to basically destroy the arguments of the quantum mechanics. It was never the purpose of this paper. Its purpose was to demonstrate, its purpose was to verify, its purpose was that the quantum mechanics that we have, it's not a complete theory, it is an incomplete theory. And the argument began with a remarkable quantum situation. Now, let's go back to that imagination as I started with the local imagination. I mean, imagine that we have two particles, and these two particles interact each other, and then they are sent in opposite directions. You have two particles interacting, and then you separate these two particles over very, very large distances. Even though they are now far apart, very far apart, quantum mechanics describes them using a single combined state, a single combined wave function. And according to theory, certain properties of two particles remain perfectly correlated. They remain intact with the particles even if you take these particles to the edges of the universe. Now suppose we measure one particle which is at the edge of the universe. Instantly, quantum mechanics tells us what result must be obtained for the particle which is on the other edge of the universe, which is extremely far away from the first particle. And Einstein found this deeply troubling. It was troubling. It was very troubling for Albert Einstein. And he asked a simple question. He asked a profound question, a simple, profound question. How does the second particle know what happened to the first particle? What happened to the first particle? How does the second particle know about that? It's like this particle has a brain, and this brain is getting some kind of instantaneous, mysterious information. Did some mysterious influence travel faster than light? So if that's true, then certainly there is a constraint. There's a trouble for special theory of relativity. So relativity appears to be in trouble in that case. Or were both particles carrying some hidden kind of information? That hidden information is amalgamated. If that's true, then quantum mechanics has omitted an important part of the reality. So what's going on here? Einstein concluded that the second explanation was far more reasonable, that there is something hidden going on. And he believed that these particles, they possessed definite properties before any measurement was taken, before any measurement took place. And he presumed it like the pair of glove, that you know that there is a pair of glove, one is right, another is left. This is how he perceived this problem. And quantum mechanics, according to him, merely failed to describe those hidden properties that was making things happen. That if you make an act of measurement on one particle, it instantaneously makes the other particle the other way. So you notice how elegant Einstein's reasoning was here. It was not the reasoning, a local kind of reasoning that people generally go with. He did not basically attack the experimental results. He did not attack those experiments. What he was trying to do is he attacked the logical completeness of quantum mechanics. He attacked the completeness of quantum theory. So what he did, he argued that if quantum mechanics predicts instantaneous correlation between distant particles, then one of the two conclusions that Einstein gave must be accepted. So what were the two conclusions? Either faster than light, faster than light influences exist, or theory is incomplete. Theory is not complete. And Einstein preferred this second argument. He preferred that quantum mechanics is not a complete theory. He did not go with the first argument because it was completely violating the special theory of relativity, that nothing can travel faster than that of speed of light. Now, Niels Bohr responded almost immediately, and his reply was subtle, and at the same point of time it was difficult. And what Bohr did, basically, Bohr argued that Einstein's reasoning relied, it intuitively, excessively, exclusively relied on classical concepts of physics. And according to Bohr, the properties of quantum systems cannot always be discussed independently. They cannot be discussed independent of the measurements that are performed on these experiments. The experimental argument is the part of complete physical description of the quantum mechanics. So this did not mean, basically, it was not something like that we cannot take it in the negative sense. This does not mean that something like human consciousness creates some kind of reality. No, it was not like that. Rather, it meant that the outcome of quantum measurement cannot always be separated from, it cannot be always be taken away from the conditions under which the measurement is made. And many physicists, they found Bohr's explanation very convincing. A good number of physicists, they found it convincing, going with that argument. And there were a good class of pupils. Others really found it frustratingly, purely philosophical, the arguments that Bohr was giving. Even today, I'll tell you frankly, readers often disagree about whether Bohr's response is immediately intuitive in nature. That's what it is. But almost, I should say, everyone agrees on a single point. Everyone has an agreement on one point. What's that? That is the paper EPR, the paper changed the direction of quantum physics. It changed the direction of quantum mechanics forever and ever and ever. What it did basically, it forced scientists to think much more deeply, to go very deeply about the meaning of measurement. The meaning of measurement, then reality, to go deep into what's information. And one of the scientists who read this paper, EPR paper, as I said, with greater interest was none other than Erwin Schrödinger. And Schrödinger recognized that Einstein had identified something extraordinary, something incredible. And what he did, he introduced a new word to describe this connection. And what he did, this mysterious connection between the distant quantum systems. What should I do? My phone is ringing. I will continue. I'll not take it right now. And what he did, he called it entanglement. He came up with the word quantum entanglement. And today, quantum entanglement is considered one of the defining features of quantum mechanics. So we can understand this entanglement word has come out of the answering of EPR paper, and Schrödinger himself described it as not merely one feature of the quantum mechanics, but the characteristic feature that distinguishes it from classical physics. What a great word, and that too is coming out when you have the greatest man questioning your arguments. To illustrate the strange implications of quantum theory, Schrödinger proposed one of the most famous experiment. This experiment is in every family in modern world. The famous experiment in the history of science. And what is this experiment? What is that? Imagine you have a sealed box. Now inside the box, you have a cat. And also inside this box is a tiny amount of radioactive material. As you know what radioactive material is, it has a half-life, it keeps on emitting those particles. Now, if one atom of that radioactive material decays during the experiment, there is a detector. A detector triggers a mechanism that breaks a vial. This vial is filled with poison. Now, if the atom does not decay, the poison remains sealed. Now, according to quantum mechanics, before the box is opened, what you have the radioactive atom. And this radioactive atom is described by the well-known quantum mechanical superposition of decayed and undecayed states. Okay, so you have the superposition of decayed and undecayed states. Now, if the measuring device is treated as a part of the quantum system, the entire system that we have talked about here, including the cat in the box, becomes mathematically linked. They are mathematically connected. Linked to that superposition. that I talked about, Schrodinger was not claiming that real cats literally exist in a practical state of being both alive and dead in any ordinary sense. The sense was not ordinary. It was quantum mechanical in nature. His purpose was to expose how difficult it is to apply quantum ideas directly to everyday objects. This was the intuition of this thought experiment. The thought experiment of all these things. This thought experiment, what it did, it challenged physicists to ask a profound question, to come up a very profound question. Where does the quantum world end and the classical world begins? This is the outcome of this experiment. I mean, when does a quantum possibility become a definite outcome? When you don't open the box, there are many possibilities. Now, is the wave function a real physical object? The mathematical wave function that we have? Or is it simply a mathematical tool for making these calculations to calculate all of these probabilities, where you have less probability of finding the particle, where you have more probability of finding the particle? These questions remain central. They remain at the core to the foundation of quantum mechanics. The basic bones, the basic bricks. So what's happened? By the mid 20th century, many physicists regarded these debates as philosophical. They thought it's all happening philosophically. People are making arguments rather than they don't have any scientific purpose. They don't make scientific sense because there seemed to be no experiment capable of distinguishing Einstein's viewpoint from the Bohr's viewpoint. And then comes the game changer. Approximately in 1960s, you have an Irish physicist, and the name of this physicist is John Bell. This man completely changed the situation. Now, Bell asked a remarkable question. See, it's all running with questions, and at the end you will come up with the question. So could one design an experiment that would decide whether Einstein's hidden variable picture that he has given or the predictions of the quantum mechanics were correct? Could we design this kind of experiment where we could exactly say who is right and who is wrong? And this was the question in the mind of this genius, John Bell. And the answer to this question, his answer transformed the entire debate. It transformed this debate from philosophical arguments that we usually have in day-to-day life into the experimental science. Science means you can verify it. And that's exactly where our next story goes. And in the next part of this video series, I'll be talking about the Bell's theorem. I'll not take into account any kind of mathematical equation over here. I'll take the account of this Bell's theorem. And this is the Bell's inequality. And it's the groundbreaking experiment of the Allen aspect, who made an experiment later, and later experimental confirmations in the modern physics that could give us some kind of conclusion that concludes about the historic Bohr-Einstein debate. So with this, I would like to stop here, and then we will go with the next part of the video in which we'll be talking about the Bell's inequality. So I hope you like it. Goodbye. Have a nice time.